So we're going to start off our second week today. We've already seen how Coulomb's law can be used to calculate electric fields, and we have distributed charges, how these distributed charges will produce an electric field. So when we are calculating the electric field, we have to respect the vectorial nature of an electric field. And the guiding principle was Coulomb's law. Now we're going to use one of the four Maxwell's equations, which is Gauss's law, to look at some interesting effects that happen in electrostatics. First of all, we would like to define the concept of an electric flux. Suppose I have a charge plus Q. Of course, it's a point charge that we're going to talk about. And if we draw the electric field lines or the electric field to this charge, we know that there are two approaches. One is that we can draw vectors whose lengths show the magnitudes and directions show the direction of the electric field. The other possibility is that we draw these so-called streamlines. This is a point charge, and we know that the electric field lines or the electric field can be sketched in this manner as well. These arrows show the sign of show the direction of the electric field. And so on. So how could I predict the magnitude of the electric field by looking at this electric field pattern? Sorry? Sorry? Length of the arrows? I mean which arrows? These arrows? These are not vectors that I've drawn. This is not a vector. This is a continuous line. A vector has a fixed length. This is not a vector that I've drawn here. I'm looking at this electric field pattern. I would like to know what the magnitude of the electric field is. फील्ड लाइंस की स्ट्रेंथ कैसे नजर आ रही है यहाँ पे? कम होती जा रही है, क्या मतलब कम होती जा रही है? अब right, so the packing of the field lines tells us what the strength of the electric field in different regions is. For example, in this region the field lines are really close. In this region, the field lines are far apart. So if I've drawn these continuous field lines in the same area, so if this is an area of interest and I draw the same area of interest here, then the number of field lines piercing this area is much smaller, which means that the packing density of the field lines is much larger in the vicinity of the charge. So the density of these lines, which is really the number of lines per unit area of the picture that I've drawn, is a measure of the electric field, the strength of the electric field. And of course these arrow signs tell us the direction of the electric field. Now these electric fields permeate in space, they are spread out in space. Okay? And we have static condition, that is the fields don't change with time. This charge is there, it remains fixed. Okay? First question. Is the field uniform in space? Is the field uniform? G. No, it's not, because the packing density is changing, so the field is stronger here. And if I would like to plot the variation of the electric field with respect to the distance from the point charge, of course I will get an inverse square dependence, completely in sync with Coulomb's law. Okay. Now these field lines are also called, they constitute what is called the electric flux from this charge. And I'll explain what this concept of electric flux means and where does this word flux really come from. Likewise, if I have a dipole, for example, a positive charge separated by a negative charge, I can also draw the electric field pattern due to this dipole. So the field lines will start at the positive charge, they will end at the negative charge. And then they will curl around in space. They will always emanate or start at the positive charge, and they will sink or they will dump down at the negative charge. So this is one possible electric field pattern due to an electric dipole. And we've already seen that outside the electric dipole, the field has a 1 over r cube dependence. And if you go far away from the electric dipole, the dependence on electric field becomes, it falls off, it tapers off very sharply as compared to 1 over r square. It falls off really sharp. So if you're really far away from the electric field, you will not see any electric field, because now what you're really seeing are two opposite charges that are close together. Okay, so that's why the field falls off sharply. And we have derived the electric field due to an electric dipole from first principles. So all of these are patterns in space, and for simple geometries you can draw the electric field lines or the flux lines by hand or by intuition or by common sense. For more complicated geometries, for example, if you have a geometry like this in which you have a positively charged sheet and you suppose you have an electric quadrupole here, a positive charge, a negative charge, a positive charge and a negative charge arranged in a square lattice. This is an electric quadrupole, and it's in the vicinity of a membrane that is positively charged. This could be a cell membrane or a fuel cell membrane, and you would like to find out the electric field in space that exists because of this distribution of charges. You might not be able to use your common sense in most cases. However, if you would like to break up this problem into just the existence of the membrane, just the existence of a positive charge, a negative charge, or a dipole or two dipoles, and then use the principle of superposition, you might be able to come up or cook up an electric field. However, softwares exist that can actually take a distribution of charges and they can use Coulomb's law to find out what the electric field in the entire region of space due to a distribution of charges. Okay, so now I would like to formalize this term electric flux. And where does this word come from? Suppose I have a pipe. I'm going to use a water analogy again, and water is flowing inside the pipe. Now there's a vector field associated with this water flow. No talking please. There's a vector field associated with the flow of water. Now the velocity is a vector field. So you can define a velocity at each point in space. And we're supposing that the velocity doesn't change with time. Okay? So if I have a uniform electric field, suppose I have a velocity field, a vector field that's uniform, which means that if I draw arrows to represent the velocity vector, the arrows have the same direction and they have the same length in all parts of space. Now this is what is meant by a uniform field. A field that does not change in space, that's a uniform field. A field that does not change in time is a static field. Okay? So we would like to stick to the proper usage of these English terms. Now we have, suppose, a hypothetical cube inside the path of the water flow. Now I draw a cube. So this is my cube. It's a hypothetical volume inside the path of the water flow. And I would like to characterize these edges by, this is a point A, this is point B, C, D, E, F and G. Okay, so these are some vertices of the cube. Now this is the hypothetical volume placed in the path of water. Now what I would like to see is that if this cube is of volume 1 meter cube, which means that each square, which is the side of the cube, has an area of 1 meter square. I would like to find out the volume of water that pierces the surface ABCD in 1 second. So I'm going to analyze this problem that I have water flow. Now I'm drawing streamlines instead of arrows. That's another legitimate way of drawing a vector field. And I have a surface that is normal to the velocity vector field. This surface is a part of a cube. It's characterized by points A, B, C and D. And the area of this surface is 1 meter square. Now what I'm interested in knowing is that there is a certain volume of water that passes through this surface per unit time. Hydrologists would call this measure Q6. The flow of water in Indus River is 5 million Q6. So this is a kind of the same measure. So I would like to find out the volume of water that pierces this hypothetical surface per unit time. What is that volume? V is the velocity, it's a uniform field. What's the area of the surface? It's 1. So in 1 second, V meters cube per second of water pierces through this surface. Because the velocity of the water is 1 meter per second, this area is 1 meter square. So the volume of water that has passed through this surface in 1 second is 1 meter cube. If I draw this cube, if I close this volume, then in 1 second, if this volume is supposedly empty and I start a stopwatch at time t equals 0, in 1 second all of this volume will be filled with water. Where this length is also 1 meter, this length is 1 meter, this length is 1 meter. Okay, because the velocity is v meters per second and this area is 1 meter square. So in 1 second, V meter cube per second of water will fill up this volume. So the volume of water that passes through this surface area is V in 1 second. V meter cube per second. And if this area is A instead, suppose this area is capital A, then the amount of water that passes through this surface area A is simply VA meters cube per second. Okay, now this VA, which is a product of the velocity, the magnitude of velocity and the surface area, is called the flux of water, or the amount of water, or the fluence of water that has gone through this area in 1 second. This is the flux or fluence of water that has passed through this surface area in 1 second. Okay? Now consider the surface area BCEF. How much water passes through this surface area in 1 second? ऊंची बोले कि सबको आवाज है. If this area is 1 meter square, if this area is A, the total volume that passes will be V times A. Now what's the volume of water that passes through a surface that is parallel to the flow? That is, consider surface BCEF. ये क्लास कितने बजे शुरू होती है यार ये वाली? कितने बजे शुरू होती है क्लास? 9 o'clock. जल्दी आ गए 40 मिनट. इनकी हाजिरी ना लगेगी इन 3 स्टूडेंट्स की. Now I have a surface that is parallel to the flow. So consider this surface BCFE. What's the amount of water that pierces this surface? आप बताओ जी. Zero, because this surface appears to be parallel to the flow of water. So water is flowing through the pipe and there is a surface that is just parallel to the flow. There is no water that is actually piercing the surface. And there is no water that is actually piercing the surface ABEG. So I have 3 kinds of surfaces here. I once again draw the vector field in terms of streamlines. And I have 3 kinds of surfaces. I have a surface that is normal to the direction of the flow. Remember, the velocity is a vector field, so I can associate a direction with the flow. So this is one kind of surface. Another surface is just parallel to the flow and is pointing in the plane of the blackboard. A third surface that I can draw is again parallel to the flow, but it is normal to the plane of the blackboard. So this is like this. So this is a horizontal plane, this is a vertical plane, this is also a vertical plane, but the water hits this hypothetical plane normally. And each one of these areas could be A. So this could be A, this could be A, this could be A. Now the flux through this surface is VA, the flux through this surface is 0, and the flux through this surface is 0. And I can denote the flux of water flow by phi. So this is 0, this phi is 0, and this phi is VA. Now what if I have another kind of surface that is not really normal but makes a certain angle with the flow of water? For example, my surface could point like this. It could be slanted. Now what's the flux through this surface? You'll have to find out what's the degree of slant. So this slant, if it's vertical, the slant is 0, and if this slant is so high that it becomes 90 degrees and it transforms into this surface, the flux becomes 0. So I would need some measure of the slant, and the flux will depend upon the angle of slant. So what kind of trigonometric function can you think of which can tell us the amount of flux? There has to be some angle here we're going to talk about. So an angle between 2 quantities. One quantity is the velocity or the vector field, and the other quantity is something that tells you what is the orientation of the area of this surface. So what we could do here is that with each one of these surfaces we could draw a vector. So if this is the direction of the plane, we can draw a vector that is normal to this plane. And since this is a vector, we put an arrow sign on top of it. Now this is also a plane and there must be a vector associated with it. So what we're doing always is that we're drawing this vector normal to the surface. So this surface is vertical, so this vector is going to point outwards. So I can't draw an arrow that's pointing outwards, so I'll just put a dot here. This is the direction of the area vector. So area has now transformed into a vector. Alright? and this vector has a magnitude. The magnitude is just the area of this plane, and the direction is normal to the area. So this area will also have a vector associated with it, and this vector is going to point in the upward direction, normal to the plane. This angle is 90 degrees. So the direction of this area vector tells you what the surface is. This vector, area vector, will likewise be at an angle theta with respect to the horizontal, and this tells you what the slant is. So if theta is 0, you get this area vector. If theta is 90 degrees, you get this area vector. Alright? So now if I have a flux and I would like to factor in this angle, I would need to use a trigonometric function. So what kind of trigonometric function comes to your mind? Cosine theta. So what I would like to do, I would like to take V, multiply it with the area A, and multiply it with cosine theta. So this is the magnitude of flux that passes through a surface. But this is just another way of writing the vector dot product with the area vector. So this is the flux of water or the fluence of water that passes through an area. Now that area can have any orientation. Alright. Likewise, we can come up with a similar quantity for electric field. The electric field is also a vector field. It has a direction and it has a magnitude, so it's a vector field. So we can define the electric flux through an area. The electric flux through an area, again denoted by phi, is simply the dot product of the electric field and the area. So this is the electric field through an area. Electric flux through an area A. Suppose my electric field is non-uniform. Okay? My electric field has a gradient, which means it's large here and it weakens as we go away. So this is a typical electric field, say for example from a point source. It just radiates out like the spokes of a wheel. Okay? Now this is the electric field. This electric field has been produced from some distribution of charges. Now what I would like to do, I would like to place a small area element, I call it A, inside space, right? So this is my A. So I have a patch. This patch will not physically exist. I break up my space into a small patches. One of these patches is shown on the blackboard. This patch has an area A. Now this area could be pointing in any direction. It has a certain magnitude, which is just the physical area, the length into the breadth of this patch, and it's pointing in a certain direction. So associated with this patch is an area vector, A vector. And how do I define this vector? I just take the surface and draw a normal to it. For example, this is one surface. I draw a normal to it, it's pointing upwards. So that normal will actually tell us what the surface is. So a normal tells us what the surface is. This surface will have a normal that is horizontal. Okay? This computer screen will have a normal, and this will define the orientation of the direction. If I turn the direction of this screen a little bit, the normal will change. The magnitude will not change because the area of this screen is not changing, but its direction is. So every area is specified by a normal vector or the area vector. So now what I could do, I would like to find out the electric field that exists at this patch. Now the electric field is different everywhere. And it's different because it's changing its magnitude and it's changing its direction everywhere in space. So if I were to draw electric field vectors to represent this electric field distribution, what I would do, here the field is stronger, so I draw bigger arrows. the electric field becomes weaker, so I draw smaller arrows. Here the electric field is even weaker, so I even draw smaller arrows. So this is an alternative depiction of the same electric field. So the electric field is strong here, the electric field is weak here. But at the point of this patch, there would be an electric field. So suppose that electric field is at this point, and I call this point P, is EP. So the flux through this yellow patch is going to be E times EP dot product with the area vector. And this is simply EP, the area, into the cosine of the angle between the area vector and the electric field at point P. So this is the flux through some area. Which area? This yellow area. I would like to put an approximate sign here. Why do I put an approximate sign? Sorry?
Not like a point.
What is not like a point? Right, because this is an area that has a certain size. And since the electric field is non-uniform, the electric field could be different at this point. It could be different here, different here, different here, different here. And if this area is bigger, then this approximation becomes a stronger approximation. It becomes more approximate. If this area patch is smaller, then this approximation tends towards an equality. Okay? So if I would just like to shrink this area, I would like to call this a dA. If I shrink this area, I would like to call it a small area. And the symbol for a small element is dA. But this is also a vector. So I multiply or take the dot product of this dA with the electric field EP. And this is the flux through the small area dA. Remember that the flux is a scalar quantity. And if the electric field has certain units, like it has the units of Newton per Coulomb, it's multiplied by area. So the units of flux are Newton meter square per Coulomb. So this is the concept of electric flux. Now suppose I have the same electric field, it's a non-uniform field once again, and now I'm going to draw a more complicated streamlines, a more complicated electric field. And now what I have is a big surface that is immersed in space inside this electric field. Okay? Now I have a pear-shaped surface, a complicated shaped surface, and it's a closed surface. Now what is meant by a closed surface? A closed surface is such that you can define an inside and an outside for a closed surface. For example, if I draw a mango. Now the surface of the mango is a closed surface because I can define an inside and an outside. Which means suppose there is some small animal that lives inside the mango. Some pest that is inside the mango and it's eating up on the pulp of the mango, and the pest would like to get out of the mango. So what the pest needs to do is that it needs to puncture the surface of the mango. So it makes a puncture on the surface and the pest can come out from the inside to the outside. But it will need to puncture the surface in order to do that. So such a surface is called a closed surface. However, if you have a surface like this, which doesn't have an inside and an outside, you can't define an inside and an outside for such a surface. This is called an open surface. And if you would like to draw the normal to this surface at some point, One possibility is the normal can be drawn like this, but the other possibility is, equally valid possibility is that you could draw the normal on the other surface. So there are two possibilities for drawing the normal for an open surface. Okay? If this is my surface, one could choose to draw the normal upwards. The other person could choose to draw the normal downwards. And they're equally legitimate. There's nothing special with up or down. However, for a closed surface, the general convention is that normals point outwards. So if this is my surface and I take the surface and I take small patches on the closed surface, so this is a patch, I can draw the normal to this patch at this point. Suppose this is a small area, delta A1. It's a vector and it's pointing outwards. So it's pointing from inside towards outside. The direction of the arrow is towards outside, G.
So what if the area is curved?
Even if the area is curved, it could be open or closed. For example, you have a balloon and you are inflating the balloon. So the balloon itself is an open surface because it has an aperture into which you blow in air. However, if you tie the aperture with a thread, it becomes a closed surface. Then you have an inside and an outside. The inside is high pressure, the outside is low pressure.
How do we draw the normal for a curved surface?
For example, if I have a curve, an open or closed? So this is a closed surface. Now there is no one normal. So you would divide this surface into small patches and draw the normal at each patch. Because it's a curved surface, you cannot define one normal. If I have a sphere, now this sphere is a closed surface, and we're talking not about the volume of the sphere but the outer surface of the sphere. Okay, so the sphere is a closed surface. Remember, I'll use these words: surface. A surface is two-dimensional. I'll use the word volume. A volume is three-dimensional. I'll use the word line. Line is one-dimensional. I'll use the word point. Point is zero-dimensional. So suppose I'm considering the surface of a sphere. Now it's a closed surface. You can't get into the sphere without rupturing the surface. Okay? Now there is no one normal. If I draw a patch here, then the normal is pointing outwards. If I draw a patch here, the normal is pointing in this direction. I draw a patch here, the normal is pointing in some other direction. I draw a patch right in front, the normal is going to point outwards. Here the normal is pointing in some other direction. At the back, the normal could be pointing in the inward direction. So the normals are pointing in different directions on the surface of the sphere. Likewise, for this curved surface, I draw many small patches, delta A2. This normal is going to point in some other direction. The area vector here is going to point in the downward direction. Here the area vector is going to point in some other direction. Delta AI, for example. So there is no one unique normal that defines a curved surface. If you have a flat surface, only then can you define one unique normal for the entire surface. But most surfaces that we're going to deal with are curved. So what you would do is you take that surface area and make small infinitesimal sections on this area and define a normal for each section. Now if this volume is bathed inside an electric field, it's immersed inside an electric field which is non-uniform. Suppose I just draw the same an electric field that pierces this closed volume, okay? Remember that this volume, whose surface is a closed surface, every volume will have at its boundary a surface. Okay? So the volume of this room is three-dimensional, but the walls are the surface of this volume. So this is a closed surface inside space, and this surface may not really exist. It could be a figment in our imagination. It could be some fictitious or hypothetical surface. But there's an electric field inside this space, and this electric field is real. The electric fields are not fictitious, they are real. They can do work on objects. You place a charge here, the charge is going to move. It's going to accelerate. So electric fields, by the way, are real. They're not fictitious. They're not a figment of our imagination. They exist. Now what we would like to do is we would like to find the flux phi through this entire closed surface. Okay? Now what we would like to do is we would like to find out the electric field at the position of each one of these patches. So the electric field is going to be different. Here if I draw the electric field, it's going to point in some direction. Suppose the electric field here is E1, shown in blue. The electric field here is E2, shown in blue. The electric field here is E3, again shown in blue. The electric field here is E4, shown in blue. So at the location of each of these patches, there is an electric field. An electric field is different from point to point. It's locally different. So what you would like to do is you would take the electric field at each point, say EI, and find its dot product with the area vector at each point, delta AI, take the dot product. Now this is a local product. This product is computed at each of these patches. So it's local. This is a local dot product. Local means you compute this dot product point to point. You move from this patch to another patch to another patch. You divide this surface area into large number of patches, find the dot product, it's a scalar. And then you add up all of these scalars. Okay, depending upon the number of patches that you have. This will approximately give you the electric field. Again approximate because these patches are of finite area. Each one of these is of finite area. And the electric field on each area is going to be different. At each location inside the area is going to be different. And the area vector is going to be different because this is really a curved surface. Okay? So what you really need to do if you would like to convert this approximation into an equality, you would like to make the patches smaller so that you don't have to worry about high curvatures of the surface or the electric field being strongly non-uniform. So when you do that, this transforms into an integral, and you would just like to find out the electric field locally and take its dot product with the small area element, which has now been written as dA, and integrate. This is the flux through the entire closed surface. The electric flux through the entire surface. So let me write this down again because it's such an important formula that we've come up. Flux through any surface, be it open, closed, it doesn't matter. Through any surface is simply the integral of the electric field at each point. It's a vector dotted with dA, and then you integrate over the entire area. Now this area could be open, it could be closed. It could be closed surface or an open surface, it doesn't matter. The same formula applies. Now let's apply this beautiful, nice formula to an interesting scenario. Suppose I have a point charge. We would always like to start up with point charges, Q. Now this charge is in space, it's a point charge, positive charge, and I would like to draw a surface area around this charge. Now in space, the easiest thing to do when you have a point charge is draw a sphere. So I would like to draw a sphere now, a hypothetical sphere. ये बातें ना करो, देखो क्या बात है, आप मुसलसल बात कर रहे हैं, मैं बहुत डिस्टर्ब हो रहा हूँ. देखिए, don't respect me, but respect this body of knowledge. Now I have a point charge in space and I would like to draw a sphere around this point charge. Now the sphere is a closed surface. And what I would like to do, I want to make my life simpler. So I would like to draw a sphere whose center is the point charge. Now I cannot draw a three-dimensional sphere on the blackboard, so I would just like to draw a section of it. So I would draw this hypothetical sphere around the point charge and it's concentric with the point charge itself. Now what I would like to do is, we know from Coulomb's law is something that we've already started off with, so let's use Coulomb's law. We know that at the surface of the sphere, the magnitude of the electric field is going to be the same, because each point on the sphere is at the same distance, small r, from the point charge. And if I would like to draw the electric field just on the sphere, it will be arrows of the same length. But will these arrows point in the same direction? तो electric field की arrows इस direction में point करेगी. Which direction? बना के दिखाओ जल्दी से. This sphere की surface पे, if I would like to draw an electric field vector on the surface of the sphere, what kind of arrow would I draw? In the direction of? It's going to point radially outward. So if I draw the electric field here and represent it by an arrow, this is the electric field. This is the electric field here. This is the electric field here, here. So all around the circle, the electric field is going to point radially outward. And the lengths of all of these arrows is the same because they're at the same distance. And what do I mean by radially outward? Which means that if I connect this point with the center, I can just extend this radius outward and the electric field will point along the radius. Okay? So this is a picture of the electric field at the sphere. Now the electric field is the same in magnitude at each of these points, but it's differing in its direction. So if I would like to find the electric field at some point P, this is point P, this of course is a vector. So what is the magnitude of this electric field? आप बताओ नाम बिल्कुल बताओ क्या हो? A levels नहीं भूलता मैं. 1/4 pi epsilon naught आगे Q R squared. और what about the direction? So I would like to give this a certain name. So I would call this direction the radial unit vector. So the radial unit vector here is pointing like this, here is pointing like this. So these are the direction of the radial unit vector. So this radial unit vector is not a constant direction vector. It changes from point to point. So at each point the radial unit vector is just pointing along the radius. So this is the electric field at any point P. Now what I would like to do, I would like to break up the surface of the sphere into small areas. So I would draw a patch here, a small patch here. And I would draw a patch here. I would draw a patch here. I will draw a patch here. So I will draw small patches everywhere on the surface. I will fill up these patches. The surface is going to be filled up with these small patches. Now each patch has an area, certain area. I call that area dA. Now it's a vector. dA is a vector. So I would like to find the magnitude of this vector. The magnitude of this vector, I just call it dA. Okay? Now I would like to find the direction of this area vector. Now each of these patches is in a different direction. Remember, the electric field is going to point radially outward on this patch, on this patch. So everywhere the electric field is pointing radially outwards, and I am drawing the electric fields by yellow arrows. So the electric field everywhere is pointing radially outward. Now on each patch the area vector is also pointing in a certain direction. Is that direction same? No, it's not the same because it's a closed curved surface. What is the direction of the area vector for each of these patches? It's going to point normally outwards. Now what is normally outwards for a sphere? It's again along the radial direction. So each one of these vectors, the area vector is going to point radially outwards. Which means that on the surface of the sphere, each vector is going to be parallel to the electric field at that point. So the area vector is also pointing in the radially outward direction, in the R direction. So we are struck by fortune here. Fortune has come here to help us because it's a nice symmetric system in which electric field is pointing radially outward and the area vectors for each of the small patches is also pointing radially outwards. Good heavens, this is a lucky situation. So it's easy to find the dot product for each patch. So if I construct the dot product for each patch, E dot dA, this is simply going to be equal to 1 over 4 pi epsilon naught Q over R squared, R unit vector dotted with dA R unit vector. So what's the dot product of a vector with itself? Of these unit vectors, just one. So if I would like to compute the flux through the sphere, the flux through the sphere due to a point charge that is placed at the surface of the sphere, this is simply going to be equal to the integral Q over 4 pi epsilon naught. Now this R square into dA, right? Now the sphere has a radius R, so this R is a constant here. Okay? If you want to find the flux through the sphere of radius R, this R is really a constant. So you have to imagine what variable is a constant here. R is not a running variable. The sphere has radius R, so it's fixed. So I can take all of this out of the integral R square dA. Now, in many problems you will have to put in limits to integration and compute the integral, but this is something really simple. What is this quantity equal to? It's the total area of the surface of the sphere, which is 4 pi R squared. So I get Q over epsilon naught as my result. This is the flux through a surface of radius R. Okay, I give you half a minute just to brood and relax and think about this, and then I'll have some beautiful illustrations of this concept, some very nice, powerful implications. Question.
Can you please explain the difference between a closed and an open surface again?
Between
A closed and an open surface.
a closed surface is something for which you can define an inside and an outside. So in order to come from the inside, the interior to the exterior, you have to pierce the surface. You have to puncture the surface. You have to pass through the surface. Whereas this doesn't happen for an open surface. You can just go around the open surface and go to the other side. There are no two sides. Okay?
But you said that a balloon is an open surface.
The balloon is an open surface, but once you've inflated this and tied its aperture, it becomes a closed surface. Now let's look at this result. The flux through a surface which has a charge inside it, placed at its center, a point charge, is just the amount of charge divided by epsilon naught. And remember, this looks like a very simple formula. And we were lucky here. There's a 4 pi that comes here and there's a 4 pi that comes out from Coulomb's law. Okay? And the 4 pi's cancel out, so the flux doesn't have the 4 pi. So there's a historic reason for keeping the 4 pi inside the Coulomb's law. It just gives you a nice formula for this law, which we'll show is a form of Gauss's law. Okay? So there was a historic reason for keeping a 4 pi inside the Coulomb's law. Now let's look at this formula. Very nice, very simple. It's the charge inside the surface divided by epsilon naught. Now consider the same charge. I have Q and I draw a surface around this charge. It's a sphere again, and the charge is at the center of the sphere. Now I draw another surface outside this surface. And if I were to draw the electric fields at this surface, the field lines will of course be radially outward. And what about this outer surface? Let's call this surface S1 and there's an outer surface S2. This S2 is the entire outer surface. What about the direction of the electric field on the outer surface? It's going to be radially outward. What about its magnitude? It's going to be the same on the outer surface. But how does it compare with the magnitude on S1? It's going to be smaller. It's going to be smaller by the square of the ratio of this distance to this distance. So it's going to be smaller. So once again I can draw arrows that are pointing radially outward, but now I'm drawing smaller length arrows because the electric field is smaller here. Again the field is pointing radially outward, nevertheless. Now if I use the same prescription as I've used before and would like to find the electric flux to surface S2, how does it compare to the electric flux to surface S1? It's going to be the same. So the flux through S1 is Q over epsilon naught. The flux through S2 is also Q over epsilon naught. If I draw any other spherical surface, large, big, small, whatever surface I draw, the flux through all of these concentric surfaces is going to be Q over epsilon naught. It's not going to change. Even though the electric field here at S1 is different from the electric field at S2, it's different at S3, it falls off radially as the distance decreases. If I were to plot the electric field versus R, this electric field, we know it drops off quadratically. But what keeps the flux constant? The charge is the same, but what if an electric field is dropping off quadratically and the flux has an electric field? The area, the surface area is increasing quadratically, 4 pi r squared. So one goes up as r squared, the other goes down as 1 over r squared. And if I take the product, both of these effects cancel out and I'm left with something that is totally independent of the radius. Okay? So the flux through all of these surfaces is going to be the same, even though the electric fields are different. Now suppose this was a light bulb. Instead of a charge, we had a light bulb here. Okay? Now if you're far away from the light bulb, the amount of energy that you receive per unit area is going to be smaller. It's going to fall off quadratically. The brightness of the bulb, as you go away from the bulb, decreases quadratically. The intensity goes off quadratically. You observing stars, you're far away from stars. Stars that start off with the same luminosity have different brightnesses as we observe them, because some stars are further away. The further away the star, the less bright would it appear, even though it might be more luminous than another star. Our star, our homely star, which is the sun, is not a very luminous star. There are other stars that are much more luminous than the sun, but it appears brighter to us because it's close to us. So if you move further away from the light bulb, the brightness of this light bulb decreases quadratically. But if you go all around the surface area, the total amount of intensity that you receive is going to be constant. If you're firing bullets at this point, then the number of bullets that you will receive if you're further away in a unit time is going to be smaller. And if this bullet is firing randomly in all possible directions. But if you have observers all around, then they will catch the same number of bullets as the observers on a smaller circle. The flux of the bullets is going to be the same. Likewise for electric field lines, the flux of the electric field, which is the electric flux, is the same on this surface, it's the same on this surface, it's the same on this surface. So this is one form of Gauss's law. The flux through a closed surface. A closed surface, remember the sphere is a closed surface, equals the amount of charge that is inside the surface at the center of the sphere divided by epsilon naught. Now this is really something quite beautiful, because what you're doing here, if you want to find out how much charge is inside, you just look at the electric flux through a surface that's outside the charge. If you want to find the charge inside this room, you find the electric flux that passes through the walls. So you're finding something that inside the volume by looking at what happens on the outer surface. This has deep implications, deep philosophical, deep cosmological implications. And this is one form of Gauss's law. But let's generalize this a little bit. Okay? The real beauty is yet to appear. Now this is slightly complicated, a slightly complicated calculation, but I try to make it as intuitive as possible for you. I'm going to generalize this. Suppose I have a point charge Q, and I draw a sphere around this point charge. Now I draw another surface outside this sphere. This surface is not a sphere. It's some pear-shaped, arbitrarily shaped curved object. Again, this is a closed surface. This is also a closed surface. This surface is S1. This surface I call S2. Both of them, by the way, are hypothetical surfaces. Now I take a small patch on S1. The area of this patch is small a. Okay? Now what I would like to do is, if this were a light bulb, and if this were some opaque object of area A, it will cast its shadow on the outer opaque object. This is another opaque object. It will cast a shadow. So the shadow of this object on the outer surface is going to be another surface. If I were to draw the shadow of this object on the outer surface, will that area generally be bigger or smaller? Bigger. So how do I draw this shadow? So I just take this point and I extrapolate the extremities or the edges of this small area okay. So this is my big area. I call this capital A. Alright. Now if this radius is small r and this distance of this big A from this point is capital R, and I suppose that this big A is also small, right? Which means that this small is really small. Okay? So I assume that this big A is also small. Okay? So let me just shade this projection. This is a projection. Remember the word projection or a shadow of this small area onto the bigger area. By the way, this is how an overhead projection system works. Now, if I would like to find the flux through this small area, that flux is going to be the electric field at this area. I call this E small r into this area A. And why don't I have a cosine theta? Because this is a sphere. On a sphere, the area normal is parallel to the electric field. So this is the flux through the small area. This is flux through A, small a. Alright? Now I would like to find the flux through capital A. So what I would need to do, I would need to find out the electric field at this point. Suppose the electric field here is E capital R. Right? It's going to be different from E small r because it's further away from the point charge. So the electric field here is going to be E capital R. And how do I calculate the flux? I multiply this with the area. And what's the area here? Capital A. But what is the relative angle between the electric field ER and this area vector? Are they still parallel? No, they're not, because this is not a sphere. This is some arbitrary curved surface. So there has to be some angle between, if I connect the center of this area, this is the radial direction, so there is some angle here, theta. So this is cosine theta. I put in a cosine theta here. So this is the flux through capital A. Okay? I'm being systematic, I'm going slow, I'm being very clear here. Now, how does E capital R relate to E small r? Are they related? If I know E small r, do I know E capital R? Please raise your hands. आप बताने की कोशिश करो, आप दोनों में से कोई. If I know, can I find out the ratio of the electric fields farther away and closer? What do the electric fields depend upon? The flux bulldog, distance squared, right? So if I were to know, so can you tell me what this ratio is? E capital R divided by E small r. Could you tell me what this ratio is going to be? It's going to be small r divided by capital R squared. Correct? So this ER is really small er into small r divided by capital R squared. Alright? We've done half of it. So this electric field is going to be smaller by the square of this factor. Correct? This is just Coulomb's law. Now I would like to find out by how much is this area, capital A, bigger than small a. Right? I have to find that out. Suppose, now this is slightly tricky but not out of this world. Suppose this outer surface were a sphere as well. So instead of being a pear-shaped object, this outer surface was also a section of a sphere, which really means that I have a point charge, I have a small sphere S1 and I have a big sphere S2. And this area is small a, and I take the projection, I get a big area, capital A. So for these spheres, could you tell what the ratio of capital A to small a would be? What is this ratio going to be equal to? अब बताओ ये रेशियो क्या होगी? सोचो, ये बेसिक कॉमन सेंस, आप जी मैट और इस तरह की चीजें करती है, उस तरह का सवाल है. This area has to be bigger than this area. How much bigger? It's just going to be bigger by capital R over small r squared. क्यों? क्योंकि अगर आप ये small patches से भर दें इस छोटे sphere को, if you fill up this small sphere with small patches and you put a light bulb here, the shadow of these small patches will overwhelm or totally fill the bigger sphere. But this smaller sphere has a radius, has an area 4 pi small r square. This bigger surface has an area 4 pi capital R square. So the ratio of these areas is capital R over small r square. So if you take a small patch here, its shadow will have a bigger area, and how big? It's capital R over small r squared. Alright? So here in this factor, this capital A is equal to small a times capital R over small r squared. Is that enough? Is that enough? Because this capital A over small a is capital R over small r squared, so capital A is just A times this. ये ratio है ना? इसी तरह ER में भी हमने small ला. So this is a ratio. But is this enough? Or there is something missing here? There is something missing here because after all, this bigger surface is not a sphere. Okay? So how do we take into account the fact that this bigger surface is not a sphere? For this I would like to draw another example. Suppose I have a sphere here. Okay? And I just pick up this surface, I pinch it from here and stretch it. So I get a surface like this. So still I have a sphere here, but this point I have picked it and stretched it. So this is flexible here. So I made this sphere go into this airfoil kind of geometry. It's an airfoil, like the wings of a plane or an egg. Now what I would like to do, suppose I draw two lines here. Now this is the surface of a sphere. But this area is not the surface of a sphere. This is some other object. Okay. Now the angle here, if this were really a sphere, then the radially outward direction would be here, and the direction that this surface area is going to make is going to be like this. So there is some angle that is created by the fact that this is not a sphere. Likewise, if I draw a small section here and I extend these points onto another section of the outer sphere, this area you observe is getting bigger here. Why is it getting bigger? Because if I draw a sphere here on the outer surface and I draw the radially outward vector, it's going to point in this direction, but now this normal to this point is going to point in this direction. So the angle between the radial vector theta has increased, which means that if this angle between the radial direction and the unit normal to a particular point of a closed surface is larger, then this area is also going to be large. Okay? So what I need to do is I need to pick up a trigonometric factor that represents this. Here everything was simple. This is a sphere and it's enclosed by an outer sphere. Okay? So the radial vector and the normal, the unit normals, the AD vectors are always parallel. So there is no concept of theta here. Theta is always 0. But that's not true for this case. Here the ratio is simply the square of the ratio of the radiuses. Here it's not that simple. Here this area is much larger than this area because the angle that is made between the radial vector and the unit normal to this point is larger. So I would like to take into account a factor that represents this, and such a factor is cosine theta, 1 over cosine theta, which means that if theta is 0, this is 1. If theta is large, this object cosine theta becomes small and 1 over cosine theta becomes large again, which actually reflects this fact. If theta is large, then the area of the shadow is also larger. So I have these surfaces that are smeared out in strange ways. If the area is larger of the shadow, then that really means that the radial vector and the normal to that point are making a bigger angle. So I have to include this factor in as well to account for the fact that the outer surface is not a sphere. So this factor comes in here, 1 over cosine theta. Now I would like to find the flux through capital A. The flux through capital A is going to be equal to E capital R capital A cosine theta. This equals E small r into R over capital R squared, coming from here, multiplied by small a into capital R over small r squared into 1 over cosine theta, coming from this capital A, and finally a cosine theta, which is due to the definition of the flux. So this goes away, and I'm left with ER small a, which is the flux through small a. Now if I take all the small patches on this surface, all the small a's on this surface, I can find the flux through S1. And if I find all the patches on the big surface, I can find the flux through S2. And both of these fluxes have to be equal, right? Because if I completely enclose this opaque object, its shadow will completely cover the outer surface. So the flux through this object has to be the same as the flux through the bigger object. which means that if I draw a charge and I draw a closed surface, which is a sphere, whose center is the location of the charge, then the flux through this charge I know is Q over epsilon naught. But I don't have to draw this surface. I can draw an arbitrarily shaped surface like this. And the charge need not be at the center of the surface. So I have a charge. I can draw different kinds of surfaces. I can draw something neat. I can draw something that is arbitrarily shaped. The charge need not be at the center of this surface. I can draw any surface that I like that encloses the charge. Whatever closed surface that my little heart chooses, I can draw such a surface. And the flux through that surface is always going to be equal to Q over epsilon naught, independent of where that charge lies inside the surface and what's the shape of the surface. Alright, so I'm going to post a homework that is going to be due next week. There's going to be a class on Wednesday. I'm going to show a demonstration inside the classroom. Go to tutorials this week. There's going to be recitation this week. And probably next week I'm also going to take a quiz. Alright, so I've also announced my office hours on the website. They're from Tuesday 10 to 12 p.m. Thank you very much. Thanks a lot.